Angles. Objectives. Draw angles in standard position. Convert between degrees and radians. Convert between degrees and radians and degrees, minutes, seconds. Find coterminal angles. Find the length of a circular arc. Find the area of a sector of a circle. Use linear and angular speed to describe motion on a circular path. Drawing angles in standard position. First, an angle is the union of two rays having a common endpoint. The endpoint is called the vertex of the angle, and the two rays are the sides of the angle. Here we see angle DEF. E is the vertex. An angle is in standard position if its vertex is located at the origin and its initial side extends along the positive x-axis. You can think of an angle as a ray that's rotating counterclockwise for a positive angle from EF to ED. If the ray has rotated clockwise, it will be a negative angle. We often use Greek letters to show an angle. Here are some common Greek letters: theta, phi, alpha, beta, and gamma. The measure of an angle is the amount of rotation from the initial side to the terminal side. There are 360 degrees in a full rotation of a ray. 1 degree would be 1/360th of a full rotation. An angle is a quadrantal angle if its terminal side lies on an axis, including 0 degrees, 90 degrees, 180 degrees, 270 degrees, or again 360 degrees. Here we can see the 4 quadrants and a ray that's rotating counterclockwise, landing on each of those axes to be a quadrantal angle. Converting between degrees and radians. What is a radian? 1 radian is the measure of a central angle of a circle that intercepts an arc equal in length to the radius of that circle. A central angle is an angle formed at the center of a circle by 2 radii. Because the total circumference equals 2 pi times the radius, a full circular rotation is 2 pi radians. Here's a table demonstrating the relationship between rotation, degrees, and radian measure. 1 full rotation is 360 degrees. This would be equal to 2 pi radians. Half of a rotation is equal to 180 degrees, which is equivalent to pi radians. A fourth of a rotation is 90 degrees, and that's equivalent to pi over 2 radians. It's important when we're talking about degree measurement that we use this degree label or write out the word degrees after the number measurement. For radians, we can either state radians or state nothing at all. If there's no unit stated, it is assumed that the measure is in radians. Relating arc lengths to radius. An arc length S is the length of the curve along the arc of a circle. S equals r theta. Theta then is S divided by r. Now here, if S equals r, then theta is equal to r over r, which is 1 radian. So how many radians will it take to get all the way around the circle? If we would lay down several of these radians going around the circle, what we would find is that it would be 1, 2, 3, 4, 5, 6, and part of a radian to get all the way around. In fact, to get halfway around would be equivalent to pi. So to get all the way around, it's going to take 2 pi radians of rotation to get all the way around the circle. Identifying special angles measured in radians. What is the radian measure of 1/3 of a full rotation? That would be 1/3 of a full rotation 2 pi. That is 1/3 times 2 pi, which is 2 pi over 3. What is the radian measure of 3/4 of a rotation? 3/4 of 2 pi is going to be 3/4 times 2 pi, which is 3 pi over 2. You can see some special angles marked here. We'll learn more about these angles and the relationships between them as we proceed through the course. Now, degrees and radians both get used to measure and describe angles, so we need to be able to convert between them. But we can do this quite easily, just multiplying by a conversion factor. I know that pi and 180 degrees are equivalent, so if I take some degree measure and I multiply it by pi times 180, we're really just multiplying by a fancy form of 1, and out will come our radian measure. If I'm in radians and I want to get to degree measure, I know that 180 degrees and pi again are equivalent, so 180 degrees divided by pi is the same as just multiplying by 1. I can take that radian measure, multiply by 180 degrees over pi, and out will come my degree measure. Let's practice this conversion. Here, convert each radian measure to degree measure. Here, I'll multiply by 180 degrees over pi. This way, my pi's will cancel out. And I know 6 goes into 180 30 times, so this is equivalent to 30 degrees. Next, I have 3 radians. Same procedure, I'll multiply by 180 degrees divided by pi. Here, there is no pi to cancel out, so I'll go ahead and put this into my calculator to get a decimal approximation. 3 times 180 divided by pi. And I get approximately 171.9. Remember to put your degree symbol to signify that that is a degree measurement. Here I have negative 3 pi over 4. With the same procedure, I'm going to multiply by 180 degrees over pi. When I put that into the calculator, or you can do this one by hand, you'll get a negative 135 degrees. Here, let's convert each degree measure to radian measure. 15 degrees, I'm going to multiply by pi over 180 degrees. This way, our degrees will cancel each other out. After simplifying, I get pi over 12 radians. 126 degrees. This could be written out as degrees, the abbreviation of DEG, or have the degree symbol. This is in degrees, so we're going to multiply by pi over 180 degrees. That way the degrees there and the degrees there cancel out. When I put this into my calculator or simplify by hand, I'm going to get 7 pi over 10. Here, negative 75 degrees, I multiply by pi over 180 degrees. Again, the degrees cancel out. When I simplify, I get a negative 5 pi over 12. Showing you how to do this on your calculator, you'd have a negative 75 divided by 180. Depending on the settings of your calculator or the model of your calculator, you may get a decimal like this. So look for a fraction to decimal conversion button. You can use that, and you'll see this is a negative 5/12 of a pi, or negative 5/12 times pi. That gives us our negative 5 pi over 12 radian measure. Even in degree measurement, we have different ways of showing what the measurement is. We could give a decimal degree, or we could give a measurement in degrees, minutes, and seconds. So a decimal degree can be expressed in degree, minutes, seconds using these fractions. We know that a minute is 1/60th of a degree, similar to a minute being 1/60th of an hour. And a second is 1/60th of a minute, or 1/3600th of a degree. Minutes are denoted with the apostrophe sign, while seconds are denoted with the double apostrophe sign. Convert a measure of 42.125 degrees to degrees, minutes, second format. I'm going to show you how to do this on the calculator as an assist. First, I know that I have 42 full degrees. So it's the 0.125 degrees that I need to convert to seconds and minutes. So let's go ahead and put 0.125. I know that is 0.125 degrees, or 0.125 times 60 to get us the number of minutes. Here we have 7 full minutes. So we'll write 7 minutes. And then if I subtract off that 7, I see that I have 0.5. That's 0.5 minutes. 0.5 minutes, we're going to multiply that by 60, since there are 60 seconds in a minute, and that gives me 30 seconds. So 42 degrees, 7 minutes, and 30 seconds. Here I'm converting 117 degrees, 15 minutes, 45 seconds to decimal degrees. I know that the full part is 117. If I have 15 minutes, that means I have 15 divided by 60, which is 0.25. And then I have 45 seconds, which is 45 divided by 60 to tell us how many minutes we have, and divide that by another 60 to tell us how many degrees we have. That's going to be 0.0125. So plus a 0.0125, we'll actually have 117.2625 degrees. Now some calculators can assist with conversions between degrees, minutes, seconds, and radians. So here let's practice converting 27.38 degrees to degrees, minutes, seconds, and then to radians using the calculator. My first step is to put 27.38. I need to communicate to the calculator that this is a degree measurement, so I'm going to hit second, and the angle menu is just under there. The first choice is degrees, so hit enter. Now go back into that angle menu, and if you scroll down, you'll see degrees, minutes, and seconds. Hit enter. So this is going to take 27.38 degrees and convert it to degrees, minutes, and seconds format. That would be 27 degrees, 22 minutes, 48 seconds. Now let me show you how to change 27.38 degrees to radians in the calculator, just using that angle menu. 27.38, again, we have to go into the angle menu to tell the calculator that this is a degree measure. And if you go ahead and hit enter, if you're in radian mode up here, it will change it. So this is approximately 0.478 radians. So let's double check this. The way that we converted to radians before was 27.38 times pi divided by 180 degrees. And exactly the same measurement comes out in radians if we did it long way on the calculator. Coterminal angles. If two angles in standard position have the same terminal side, they are coterminal angles. Any angle has infinitely many coterminal angles because we add or subtract 360 degrees, or 2 pi if working in radians, to that angle, resulting in an angle with the same terminal side. Here we see coterminal angles of 38 degrees and negative 322 degrees. Find an angle theta that is coterminal with an angle measuring 870 degrees, where theta lies between 0 degrees and 360 degrees. So we'll take 870 degrees and we'll subtract 360 degrees as many times as we need to get an angle between 0 and 360 degrees. Using our calculator, we have 870. We'll subtract off 360. And we'll subtract off another 360 degrees. And that gives us an angle measure that is between 0 degrees and 360 degrees. Find an angle beta that is coterminal with an angle measuring negative 300 degrees, such that beta lies between 0 and 360 degrees. Here, we'll need to add 360 degrees. When we do that, we get 60 degrees, which is our coterminal angle between 0 and 360 degrees. Find an angle beta that is coterminal with 19 pi over 4, where beta lies between 0 and 2 pi. So starting with 19 pi over 4, we need to subtract 2 pi off as many times as we need to so that the angle is between 0 and 2 pi radians. We can use our calculator to help us with this. So we'll start with 19 fourths. We know that's 19 fourths pi. and we'll subtract 2 off. That's still more than 2, as in 2 pi's. Let's subtract another 2. That's 0.75. And we can convert that to fraction form, which is 3/4 of a pi. So we subtracted off 2 pi 2 times, and we got 3 pi over 4. Let's find an angle measure of theta that's coterminal with an angle of measure negative 17 pi over 6, but where theta lies between 0 and 2 pi. So I have a negative 17 pi over 6, and I'm going to add 2 pi as many times as I need in order to get the angle between 0 and 2 pi. We'll use our calculator again to help us with this. Entering negative 17/6, and we know that's the coefficient of pi, and I'm going to add 2. That number is not between 0 and 2 pi, so I'm going to go ahead and add another 2 pi. So I'm adding 2, and that is going to be between 0 and 2 pi. Now let's convert this to fraction form, and this is 1 1/6. We can convert that again to an improper fraction. So this is 7 pi over 6. Remember, when we're doing this on the calculator, we're only looking at the coefficient of pi so that everything stays in terms of pi. Length of an arc. In a circle of radius r, the length of an arc subtended or spanned by an angle with measure theta in radians is S equals r times theta. Just note, theta must be in radians. Find the arc length along a circle of radius 10 inches subtended by an angle of 215 degrees. Now, we noted that theta must be in radians, so our first order of business is to change 215 degrees to a radian measure. To do this, I'm multiplying by pi over 180 degrees. That way, the degrees cancel. Now, using my calculator, I can put 215 divided by 180, and I can turn that into a fraction. That gives me 1 7/36. I'm going to change that into an improper fraction. I have 43/36 pi. So we have 43 pi over 36. Now that I have my radian measure, I can use the formula S equals r times theta. The arc length is the radius, which we know is 10, times theta in radians, which is 43 pi over 36. And I can put that into the calculator. Just going to take my previous answer and multiply it by 10. Again, you can change to improper fraction form. So this is going to be 215 pi over 18. I can multiply this now by pi, and this will give me a fraction, but we can change that to decimal form. So it's approximately 37.52, and this will be in inches, the same unit as the radius. Now there's a setting on your calculator that can help you simplify some of your steps. Might have to check and see where it is on your particular model, but if I had something like the 215 over 18, and my calculator has given that to me as a mixed number, in the mode, move down the menu, there is a setting where you can always have numerator over denominator form instead of mixed number form. So you can see if I had done the calculation that I did before, the 215 over 18, there we go. If I had 11 and 17/18, hit enter, it'll automatically put it into improper fraction form for you, which for us in algebra and trigonometry is a lot better than a mixed number when we're working with anything other than a practical application problem. Assume the orbit of Mercury around the Sun is a perfect circle. Mercury is approximately 36 million miles from the Sun. In 1 Earth day, Mercury completes 0.0114 of its total revolution. Determine the radian measure for Mercury's movement in 1 Earth day. That theta is going to be 0.0114 of a full revolution to pi. So I can put this into the calculator, 0.0114 times 2 pi, and this gives me a decimal approximation of 0.0716 radians. Now, how many miles does it travel in 1 day? This is the radian measure in 1 day, so how many miles will that be? S, the arc length, is equal to the radius times theta in radians. So I know that my radius is going to be 36 million, and my theta, I just figured, is 0.0716 radians. Now, when I put this into the calculator, I'm going to make sure and use the number that is in my calculator rather than just the number that I've reported on paper here. That will help us to avoid round-off error. So I'm taking this and multiplying by 36 million. And I get about 2,578,619.25 miles. We could also use angles to find the area of a sector of a circle. A sector is a region of a circle bounded by 2 radii and the intercepted arc, kind of like a piece of pie. Here we have the area equals 1/2 times theta times the radius squared. How have we come to that formula? Well, I know that the area of a circle is pi r squared. And the angle that I've gone around in my rotation is some theta part of a full 2 pi rotation. So if I multiply those both together, that gives me theta times pi r squared over 2 pi. And some simplification will bring me to 1/2 theta r squared. In central pivot irrigation, a large irrigation pipe on wheels rotates around a center point. A farmer has a central pivot system with a radius of 400 meters. If water restrictions only allow her to water 150,000 square meters a day, what angle should she set the system to cover? In the end, convert your answer to degree measure. Well, I know the area of a sector is 1/2 theta r squared. I know that I have 150,000 square meter limit on the area to be able to water. Fill in the rest of the formula. That's half times theta, which is what we're going to be solving for, and the radius is 400. We'll square that radius as the formula shows us. This gives me 150,000 equals theta times 80,000. When I divide this, both sides, by 80,000, I get 1.875 radians. So that's my radian measure. Let's go ahead and convert that to degree measure. 1.875 radians times 180 degrees divided by pi. When I put this into the calculator, I get about 107.4 degrees. Linear and angular speed describing motion on a circular path. An object traveling in a circular path has two types of speed. Linear speed, denoted by lowercase letter v, is the speed along a straight path and can be determined by the distance it moves along, in other words, its displacement, in a given time interval. The resulting speed will be the length unit used for the radius and the time unit used. This is very similar to the rate equals the distance divided by time. Now, angular speed, lowercase Greek letter omega, results from circular motion and can be determined by the angle through which a point rotates in a given time interval. The resulting speed will be in radians per time unit. Combining the definition of angular speed with the arc length equation S equals r theta, we can find a relationship between angular and linear speeds. The angular speed equation can be solved for theta, giving theta equals omega t. Now substituting this into the arc length equation gives S equals r theta, which is r times omega t. And substituting this into the linear speed equation gives v equals s over t equals r omega t over t, which is r times omega. Just a note, theta must be in radians when we're using these formulas. An old vinyl record is played on a turntable rotating clockwise at a rate of 45 rotations per minute. Find the angular speed in radians per second. I know that omega is equal to theta divided by t. I know omega then is going to be equal to 45 2 pi rotations divided by 1 minute. This uses 45 rotations per minute, that piece of information. Now, 90 pi radians per minute is my omega. If I multiply that by 1 minute over 60 seconds, this is going to convert this to be radians per second. This will end up as 3 pi over 2 radians per second. If we put this into the calculator, just 3 times pi divided by 2, we could get an approximation. This is about 4.71 radians per second. A satellite is rotating around the Earth at 0.25 radians per hour at an altitude of 242 kilometers above Earth. If the radius of the Earth is 6,378 kilometers, find the linear speed of the satellite in kilometers per hour. Here I have the Earth with a radius of 6,378, and then I have the orbit of this satellite that is 242 kilometers above the Earth. So we have a total here of a radius of 6,620 kilometers from the center of the Earth. Now, I know my omega is 0.25 radians per hour, and V is R times omega. So my speed, my linear speed, is going to be that 6,620 times the omega, which is 0.25 radians per hour. And when I put this into the calculator, I get 1,655 kilometers per hour for the linear speed.